All right, next up what we're going to do is find the Laplace transform. We want to evaluate the Laplace transform of cosine and sine. So let's find the Laplace transform of cosine. I'm just going to do cosine of kt, where k is a constant. I'm going to call this value I. And we'll find the Laplace transform of sine of kt. Once we know one, we'll know the other. We'll see how this works. I'm going to call this j, just for convenience. And what we're going to do is we're just going to evaluate this using the definition. Okay, so using our definition that we have. And we're just going to get to work. So it turns out, if we just plug in, just by definition, if we let f of t be cosine of kt, we end up with the integral from 0 to infinity, e to the negative st, cosine of kt dt. And what we're going to do is going to be calc 2-ish. We're going to do some integration by parts, and we'll see exactly how this works. And then I'll show you a nice, kind of a real nice, cleaner way to do this. But we need a little bit of a setup before we do it a second way. So I want to actually go through, appreciate how nice the second way is going to be. And we're going to go through and find this. So this is just going to be found via integration by parts. It might be worth just writing real quick for integration by parts. If we have the integral of f prime g, that's fg minus the integral of fg prime. Okay, so that's the kind of working formula I have of integration by parts. Okay, and we've talked about that previously. So what we're going to do is apply integration by parts here. And what I want to do is it's actually not going to matter which one you pick to be f prime and which one you pick to be g, but let's just call the e to the minus st, let's call this g. So this is our g. And then that would make cosine of kt our f prime. Some books like to call f prime, they like to call it dv, and they like to call g u. So there's also, remember, the second formulation, where if you have u dv, that's equal to uv and minus integral of v du. So some books like to write it like that. That's really just the same differential, integration by parts formula using differential notation. Anyways, so if we set this up, we're going to have that our integral is going to be equal to, let's see, so we're going to integrate cosine of kt. So that means that we're going to end up with 1 over k sine of kt e to the minus st as t goes from 0 to infinity. And then this is going to be minus the integral from 0 to infinity of f, let's see, it's f times g prime. So our f is again 1 over k sine of kt, so 1 over k sine of kt, times the derivative, so times the derivative of g, so that's the derivative with respect to t. So we're going to end up with minus s e to the minus st dt. I'm not going to write out the limit as n goes to infinity and think of these as limits of finite integrals over finite intervals. We're just going to do the usual let t go to infinity, let t go to 0 thing. So for starters, as t goes to infinity, this exponential term is going to go to 0, and the sine term is going to be fixed. 1 over k is a constant, so that's going to be 0. And when t is equal to 0, we get 0. So this first expression actually turns out to be 0. The second expression that we have, let's bring out the constants. This is going to be minus 1 over k times a minus s times the integral from 0 to infinity e to the minus st sine of kt dt. Okay, just looking at that, and that turns out to be s over k times j, right, where j was the Fourier transform of sine of kt. Excuse me. And so let's just write that down. That's important. I is s over k times j. Okay. And what we're going to do then is, that's why knowing one is enough to know the other. So now we need to find j. So let's write this out. So j is going to be the integral from 0 to infinity e to the negative st sine of kt dt. So we just need to go through and find this. And we're going to do a very similar thing here. We're going to do integration by parts again. We're going to end up with, let's see, if we integrate sine of kt, so I'm thinking of sine of kt as our f prime. If we integrate that, we're going to end up with negative 1 over k cosine of kt, and then that's times e to the negative st. That's from t equals 0 to infinity, minus the integral of, let's see, we're going to have, so the integral from 0 to infinity, negative 1 over k cosine of kt times minus s e to the negative st dt. And so that means that we're going to end up with, let's see, for this first expression, as t goes to infinity, this exponential is going to go to 0. Cosine is bounded, so this is going to go to 0 by the squeeze theorem. And let's see, if we plug in t equals 0, we're going to get cosine of 0, which is 1. And so we'll get cosine of 0, e to the 0. So that's going to be minus 1 over k. Okay, I'm sorry, that's we're subtracting it, so that makes it minus a negative 1 over k, so that's plus 1 over k. Okay, and for this middle part, we're going to have, let's see, negative 1 over k and minus s. Those signs are going to cancel. This is going to be minus s over k times the integral from 0 to infinity of, let's see, e to the negative st cosine of kt dt. So that means that we end up with, this means that j is equal to 1 over k minus s over k times I. And what we can do now is we can combine our two formulas for I and j and to a single formula. So I is going to be s over k times j, and j we said was 1 over k minus s over k times I. And what we can do now is solve for I. This is a perfectly straightforward algebra exercise. We're going to end up with I is s over k squared plus s squared over k squared times I. Let's, what's going to be the easiest here? Let's subtract s squared over k squared I from both sides. So that means that we're going to have I minus s squared over k squared I. That's going to be equal to s over k squared. I'm going to factor out the I. What happened here? Something is wrong. When I distributed, I'm just going a little too quick here. When I distributed, there should be s over k minus s over k, so that should be a minus. So when I move it over, that's a plus. And then if we factor out an I, we're going to be left with 1 plus s squared over k squared. That's going to be equal to s over k squared. And that means that I is going to be s over k squared. Let me actually do one extra step here. Let me just write, just so that it's completely obvious where everything comes from, I'm going to write 1 is k squared over k squared. So that makes this k squared plus s squared over k squared is equal to s over k squared. And now I'm going to multiply both sides by k squared over s squared plus k squared. And so that means that I is going to end up being s over s squared plus k squared. And therefore j is k over s times I. If we just go through and solve for j here. So j is k over s times I, and that means that j is going to be k over s squared plus k squared. So what we've just shown is two Laplace transforms. The Laplace transform of two separate but related functions. We just showed that the Laplace transform of cosine of kt, that's what we're calling I, that's s over s squared plus k squared, and the Laplace transform of sine of kt, That's k over s squared plus k squared. These are valid for all s. Oops, excuse me. These are valid for all s. I'm not going to worry too much about keeping track of the s's. I will maybe just a little bit just to show where it comes up. But basically when we use these to solve differential equations, we're not going to worry too much about that. Okay, but now we have two more functions for our list. So notice that now we have three functions total. We saw previously that if we take the Laplace transform of any function, or any constant rather, say k, that this is going to be k over s, and that's valid if and only if s is positive. Okay, so now we have three functions on our list. The more functions we have on our list, the more useful the method of Laplace transforms are going to be. So we're going to spend some time working on finding Laplace transforms of a few more functions. And then once we have a few more functions under our belt, we'll go back and we'll talk about some applications to differential equations.